All right, welcome to this explainer on automata theory, specifically course ITPCC509. Now, I want you to think of this not just as another class you have to get through, but as a real epic quest into the absolute limits of what computers, compilers, and even artificial intelligence can and cannot do. We're literally diving into the very DNA of computation today. Okay, let's dive into this. Here's our blueprint for the course, so you know exactly how we'll conquer this syllabus together. We're going to hit the foundations of formal languages, move into finite automata and grammars, level up to push-down and Turing machines, explore real-world automata applications, and wrap it all up with course logistics and grading. Section 1. Foundations of Formal Languages. To really grasp the mathematical language that machines speak, and to wrap your head around algorithmic complexity, you're going to rely heavily on your prerequisite for this course, Engineering Mathematics 3. Now, this is our escalation sequence. Throughout the course, we're basically going to keep leveling up our computational models following what's known as the Chomsky hierarchy. We start at level 1 with finite automata, which is the absolute simplest form of machine memory. From there, we graduate to push-down automata to add some complex structural memory, and then we hit the theoretical peak of computation, Turing machines. Section 2, Finite Automata and Grammars. So this is that first level of our theoretical machine hierarchy. Before we even think about writing code, we have to strip things down to the absolute basics. I'm talking alphabets, strings, and regular expressions. When we look at how machines actually make decisions, which is course objective 2, by the way, we have to compare deterministic and non-deterministic finite automata to see how they efficiently recognize languages. So, in a deterministic model, a DFA, for any given state and input, there is exactly one next state. It's totally locked in. But non-deterministic models, the NFAs, they can guess. They can literally take multiple paths all at once. Figuring out how to convert between these two models is a huge part of this module. And this brilliantly illustrates the core difference when these finite state machines actually spit out an output. Moore versus Mealy machines. With Moore machines, your output depends entirely on the current state. That's it. But with Mealy machines, the output looks at both the state and the current input. What does that mean? Well, it usually means they can respond a lot faster, using fewer states. You'll learn how to convert between these two models, which is absolutely crucial for real-world systems. Actually, think about stuff you use every day, like vending machines or traffic light controllers. They run on these exact principles. Section 3. Pushdown and Turing machines. Okay, so basic finite automata are great, but they can't count indefinitely because they don't have structural memory. So it's time to add memory and overcome those limitations. This is exactly where context-free grammars and push-down automata, or PDAs, step in. By using a single-stack memory, honestly, just picture a stack of heavy plates where you can only add or remove a plate from the very top. PDAs can recognize context-free languages, and this ties right into a self-learning topic from your syllabus, designing programming language interpreters and syntax parsing. Every single time you write a block of code in Java or Python and the compiler checks if your syntax is right, it's basically using the logic of a push-down automata to parse through those complex nested structures. But, that leads us to this massive, kind of mind-bending question. Can a machine solve every single problem in the universe? Take a second to really think about that. If we give a machine enough memory and an infinite amount of time, is there any problem it literally cannot compute? Well, as we shift into Module 5, we introduce the universal Turing machine, and we finally confront the ultimate boundaries of computing reality. And the answer to that huge question lies right here with the halting problem. It turns out, no, machines absolutely cannot solve everything. The halting problem uses a formal proof, specifically a diagonalization argument, to demonstrate undecidability. It proves that it is mathematically impossible to write a master algorithm that can definitively tell you if a program will eventually stop or just run forever in an infinite loop. This isn't just a simple hardware limitation. It fundamentally limits what algorithms can ever achieve, no matter how advanced our AI gets. Section 4. Real-world automata applications. Okay, let's shift gears from the heavy theory to practice and tackle the big "so what" factor by jumping into Module 6. Because the theory you're learning here actually gives you practical superpowers. Finite automata, that is the engine behind compiler lexical analysis and pattern matching for search algorithms. Pushdown automata, that's what allows for balanced parentheses checking, essential stuff for building Python or Java interpreters. Context-free grammars are used in natural language processing to model human syntax. And as a self-learning topic, you'll even explore how finite automata powers intrusion detection systems in network security. Basically, these abstract theoretical models are the hidden engines running modern tech. Section 5. Course Logistics and Grading. Look, mastering the theory is really only half the battle. Now we need to map out exactly how you're going to pass this class. First off, this course carries a weight of 3 credits. It is a professional core course, which means it's absolutely foundational to your engineering degree. It demands your focus because the concepts you pick up here are going to ripple through the rest of your coursework. So the crucial point is how these 100 total marks are actually divided up. It's a perfectly even split. 50 marks for your in-semester assessment and 50 marks for the end-semester examination. You definitely cannot just coast through the semester and hope to cram for the final, but you also can't ace the midterms and sleepwalk through the end of the year. Your effort has to be balanced the whole way through. Now, let's break down that 20-mark continuous assessment part of your semester, because it is highly specific. You've got 5 marks coming from an MCQ test that's modeled right on the GATE exam pattern. Another 5 marks are earned through an article reading and report writing exercise. You'll snag 5 more for a class test, and the final 5, that's just for regularity. Showing up and engaging literally builds your grades step by step. Let's move on and see how this builds your final exam strategy. For that 50-mark end-semester exam, please don't expect an even review of the whole year. Only 20 to 30% of the final covers the pre-mid-semester syllabus. Meanwhile, a massive 70 to 80% of the exam focuses on the post-mid-semester syllabus. So the bulk of your final grade is heavily weighted toward the later, much more complex modules like push-down automata and Turing machines. To really conquer this material, you're gonna need the right tools. For essential reading, the syllabus calls out texts by J.C. Martin and Kabi Mahesh. But hey, if you're a visual learner and want to dig a bit deeper, we highly recommend checking out the NPTEL online video courses from IIT Kharagpur and IIT Madras. They are incredible resources for helping you visualize these abstract machines. So we've covered the foundations, the machines, the impossible problems, and exactly how you'll be graded. By understanding the real boundaries of computational systems, you aren't just learning how computers work today, you are literally learning the framework for future innovation. So I'll leave you with this to think about. As artificial intelligence continues to rapidly push our current boundaries, which computational limits will you redefine with this knowledge? Thanks for joining this explainer, and seriously, good luck on your exploration.